Good morning. Today is April 19, 2020, and once again, this is Teacher Ariel. Our subject is measurements and experiments. Our topic for today is a continuation of the voltage divider circuit of resistors. Here are the objectives, and these objectives were explained in our previous lesson, so we will skip this slide. We will proceed to the next slide. So this is the formula that we're going to use to find out the individual voltage drop of our lesson for today. So Vn, meaning this is the voltage drop of a specific resistor, like for example voltage drop in R1. So we will be dealing like R1. So the formula is Rn, which is the specific resistor, divided by total resistance times the total voltage. Like for example, we are going to find out voltage drop in R1. So voltage drop in R1 is equal to R1 divided by total resistance times the total voltage. So you may focus your attention on this formula because you are going to use this in our computations, especially in your assignment. Okay? So here is the circuit. Since this is the continuation of our topic last week, and as I've said, we're going to deal with 3 resistors in this presentation. So we have R1, R2, and R3. So the supply voltage is 10 volts, or the total voltage is 10 volts, and the resistance in R1 is 130 ohms, R2 is 510 ohms, and R3 is 750 ohms. Again, in voltage divider circuit, we are dealing with a series circuit, resistors which are connected in series, to make it clear. Here are the computations. So here is the circuit. We have 10 volts. We have R1, R2, and R3 with specific resistances. Now let us proceed to finding the voltage drop across R1. So the formula is voltage drop across R1 is equal to total voltage times R1 divided by total resistance. So R1 is equal to 10 volts times 130 ohms divided by 1390. So the voltage drop in R1 is 0.93 volts. Next, voltage drop in R2 is equal to total voltage, which is 10 volts, times R2 divided by total resistance. So voltage drop across R2 is equal to 10 volts times 510 ohms divided by 1390 ohms. So the voltage drop across R2 is 3.69 volts. Then voltage drop across R3 is equal to total voltage times R3 divided by total resistance. VR3, or voltage drop across R3, is equal to 10 volts times 750 ohms divided by 1390 ohms is equal to 5.39 volts. To sum it up, total voltage is equal to voltage in R1 plus voltage in R2 plus voltage in R3, which are equivalent of 0.93 volts plus 3.66 volts plus 5.39 volts is equal to 10 volts, which is equal to the supply voltage or the total voltage. So we can also use another system using Ohm's law to solve for the individual voltage drop. Again, here are the steps in solving the individual voltage drop. First, you will be looking or finding for the total resistance, which is the formula for it is total resistance is equal to R1 plus R2 plus R3. Then the second step is solve the total current. So the formula for total current is equal to total voltage divided by total resistance. Then solve for the voltage drop across R1, which is VR1, or voltage drop across R1 is equal to total current times R1. Next, solve for the voltage drop across R2. The formula for voltage drop across R2 is equal to total current times R2. Then, fifth, solve for the voltage drop across R3. The formula for voltage in computing for voltage drop across R3 is equal to IT, or total current times R3. Why all IT? Again, it was explained our topic last week that in series circuit, the current throughout the circuit is the same or are the same. So IT is equal to IR1 equal to IR2 equal to IR3. Okay? Just a simple reminder of these formulas. Now, so the total resistance is equal to 1,390 ohms and IT is equal to 10 volts divided by 1,390 ohms is equal to 0.0072 ampere. So voltage drop across R1 is equal to 0.0072 ampere times 130 ohms is equal to 0.93 volts. Then voltage drop across R2 is equal to 0.0072 ampere times 510 ohms is equal to 3.69 volts. And number 5, voltage drop across R3 is equal to 0.0072 ampere times 750 ohms is equal to 5.39 volts. So if you're going to add or sum it up, add this voltages, we have the formula of total voltage is equal to voltage in R1 plus voltage in R2 plus voltage in R3 is equal to total voltage is equal to 0.93 volts plus 3.68 or 69 volts plus 5.39 volts is equal to 10 volts, which is also equal to the input voltage or the supply voltage. So this is also another way of computing for the voltage drop of the resistors connected in series using the Ohm's law or the formula which I had given to you a while ago. So let us proceed to the practical experiment to prove the theoretical aspect in this presentation. Let us see in practical experiment if they are the same. So I have here a breadboard consisting the 3 resistors which was presented to you in the presentation. We have 130 ohms, 510 ohms, and 750 ohms. So first we will measure the total resistance. So we will use times 100 to measure the total resistance. So we need to calibrate the ohmmeter. Okay, since this multimeter, we will use this as ohmmeter, so we need to calibrate it. So we need to make sure that the pointer lies at the 0 position on the right side of the scale plate. Okay, so let us measure the total resistance. So the total resistance is 14 times 100, we have 1,400 ohms. Again, so the total resistance is 1,400 because this is 14 times 100 is 1,400. So the total resistance again is 1,400, which is near to 1,390 ohms in our computation. Now, let us supply it with a voltage of 10 volts. So this is our power supply. We will put 10 volts as our input voltage or supply voltage. So we have here the negative, positive, and put it here. And also connect it to the negative. So since we are going to measure the voltage drop of the individual resistors, so we will set this to voltmeter. Okay, so to be safe, we will use range 12. And when using this analog multimeter as a voltmeter or in measuring voltage, we need to be very careful of the polarity. So this is R1, so we need to measure the voltage drop across R1. This is R2, we need to measure the voltage drop across R2 as well as R3. So let us now put the supply voltage. Then let us measure the voltage drop across R1. So the voltage drop across R1 is 0.9 or approximately 1 volt or 0.9 volts. Okay, as you can see, that is 0.9 volts. So why? 0.2, 0.2, 0.4, 0.6, 0.8, and at the middle of 0.8 and 1, so we have 0.9 volts approximately, which is also the same as our computation, which is 0.93 volts. Okay, then let us proceed to measure the voltage drop across R2. So the voltage drop across R2 is 3.7 volts DC, which is also almost the same as the 3.69 or 3.68 volts in our computation. So why? So 3, 3.2, 3.4, 3.6, and almost near to 3.8. So that is the voltage drop across R2. So 3.7. It's at the middle of 3.6 and 3.8. Then let us proceed to the voltage drop across R3. Okay, so this is R3. So our voltage drop is 6.4. Okay, I mean 5.4. Sorry, 5.4. So 5, 5.2, and 5.4, which is also near to the computed value of VR3. Now let us check the total voltage. So the total voltage is 10 volts because the total voltage is equal to the voltage in R1 plus voltage in R2 plus voltage in R3. So we have 10 volts here. So once again, we have proven that the theoretical computations that we presented a while ago is the same as the practical application or the practical experiment of this topic. Okay? So assignment. Please use the formula that was given to you in the previous presentation in solving for the voltage in R1, voltage in R2, and voltage in R3, or should we say the individual voltage drop in this circuit. So the given voltage is 15 volts, R1 is 1K, R2 is 2.5K, and R3 is 1.5K. This assignment will be submitted again to me in our WhatsApp group, and this will serve as your activity and your attendance by the next week. Okay? So our next week topic will be current divider circuit of resistors. Again, our next week topic will be current divider circuit of resistors. And thank you very much and have a nice day.